this. See, in today's live, we are going to analyze Schrödinger's equation, not the exact and the whole story related to Schrödinger equation, but what is Schrödinger equation, where it is to used, and what are its forms, time independent and time dependent. Now see here. Now see here. As we know, first of all, a little bit brief explanation to Schrödinger equation. What is Schrödinger equation and why Schrödinger equation is useful in quantum mechanics? Schrödinger equation, Erwin Schrödinger first analyzed the subatomic particles or the quantum particles which are very small, in a wave equation. Before Schrödinger, de Broglie or Max Planck or Max Born or Bohr, Niels Bohr, they analyzed that subatomic particle has particle nature and wave nature, wave-particle duality, and how it behaves when it will be a wave. When we think particle as a wave, Schrödinger was the first to design a wave equation that is different than classical wave equation to the particles. Means the wave possessed by particles is matter wave, and his equations are analyzing matter waves. So Schrödinger equation is the not classical, but it's non-relativistic wave equation of matter waves. Matter waves means particles, subatomic particles, so wave nature, and that wave is matter wave. See here. This wave function is the matter wave function. Means this, if you are seeing this, it means that this is showing the nature, the behavior of any particle. It is showing how many? 5. Whenever we see this function, this function is a matter wave function. Means this function is representing the wave of subatomic particles like electrons, protons, this. So whenever we see this is matter wave function, this represents electrons, protons, or whatever subatomic particles are.
So there's a comment at the rate Ilham Khalil 8366. He's saying hi.
Oh, hi. Thanks for watching. You are in the live. And today's live is related to Schrödinger equation. Okay, if you have any question, you can ask me, or if you have any suggestion, then you can deliver to me. See here. This is matter wave function. And this function is representing the wave pattern, matter wave pattern by the subatomic particle, electrons, protons of this. And Schrödinger made a wave that contains this function. That wave is this. This is time dependent. Why we call it time dependent wave function? Because why? In this equation you can see there is time. Means this equation, this form of Schrödinger equation is being affected by the time. Means time is important here. What is this equation? Minus h cross squared by 2m, second order derivative to the function, matter wave function with respect to the space in x-axis, If you're working on y-axis, or if you're working on z-axis, then you have to do this. Plus, there is a potential energy disturbing that particle into the wave function is equals to I h cross and the derivative of wave function with respect to time. And time is important here. That's why we call it time-independent equation. Understood? Now see, the value of this wave function, this matter wave function, this is the matter wave. This has always this form, means the matter wave function has always this type of form, means this is the amplitude, this is the amplitude. As we are familiar with the classical wave, in which we have a wave like this, so we call it amplitude, and this part as phase. Similarly, this part is amplitude in matter wave function, and this part behaves as the phase, and the phase part has time. This part has time, means this is dependent on time, and amplitude means in whatever time we are measuring, we are calculating, the wave function is this.
See, this is the same person is asking, could space-time itself emerge from the quantum state? Yes, the space.
See, I'm glad that you commented and you asked a question that is space-time emerged from the quantum space.
Yeah.
First of all, no, quantum space is itself a space which has some information in it. And if you think deeply into this, that space and time are not separate. They are the two faces of the same part. And in fact, I believe that the time is the change in space. So to understand this, we have to understand what is quantum space. First of all, quantum space, quantum state or quantum space where the particle evolves, there is no information about the quantum space, that how it behaves and what is in it. So we have to explain quantum space more and more. It's not, a state is one point of quantum space. So in the quantum space, there is the space, the geometric space, and there is time. In the geometric space, there is time inherited to this. Time is a change in the geometric space. And for that, we have to go for extremely deeper quantum calculations. So this is our amplitude. Means, remember one thing, we cannot measure quantum particles, we cannot measure matter wave function exactly, or we cannot detect. There are two parts. We always detect the amplitude, not this time part. We cannot plot this. And in that specific time, the time which is specific here, within that specific time, whatever we can detect, that is this space, this amplitude. And that's why we only figure it out. And that's why time-dependent equation in quantum mechanics, the time-dependent equation has very confusing analysis, that if we cannot use that time, if we cannot say anything about time, then how can we measure that wave? How can we detect that wave? And that's why they thought that to make it easier, we should derive an equation which has no time. From the same time-dependent quantum Schrödinger equation, they derived independent Schrödinger equation, and this is very easy to understand the quantum particles because why? It has no time, and it is it looks like as classical wave equation. Due to the time, the analysis or interpretation of matter wave was very tough. But without time, they can deliver one. They have no information of the time, but they can deliver one information about the space.
So yes, you can say the space-time itself emerged from the quantum state. Yes, quantum state is the
No, it's not clear. I cannot say that the quantum state, space-time emerge from the quantum. No, I cannot say that. These are very deep topics. We have to go deep into deep. And I personally feel the quantum state is nothing. It's not a physical state. It's just a lot of information. Whatever information you gather about that particle's wave, from the matter wave of the particle, whatever information you have, that is a quantum state. So, quantum state is just information. It's not physically existing there. What exists, that is space-time. And I can say, or my works are related to, I'm working over it, that quantum state is itself the member of a space-time. Maybe I believe in this. Because nobody tells you the what is moving in quantum state. What is flowing through the quantum state and what quantum state carries there. So the main thing is here means to make this easier, just to give you information about the space of matter wave, the spatial behavior of matter wave, we use time-independent equation. But the main equation of matter wave is time-dependent equation in non-relativistic case. In relativistic case, we use Dirac's equation. And I have works over it.
He is saying, okay, your answers make sense and I find it interesting. Appreciate
Okay,
it.
thanks for you. See, remember one thing, my friends, remember one thing. Quantum mechanics is highly uncertain. So, if you are getting any information in any book or any website from any source and you should believe it, no. I tell you to judge over it, to read over it for years, more than years. Then you have some conclusion, because quantum physics is very uncertain. And I personally working over it to make it less uncertain and move towards the certainty. My future works based over this, will be based over this. Now see here. In this live, I'm trying to tell you difference between time dependent and time independent. And so, how we derive time independent equation from time dependent equation. Now see here. How many? Okay. See this. First time writing the time dependent equation. See.
See.
This and or let me do it here because I have less space now. I'm already working, yes. Screen shaking. It's too broad now. How many people watching? Okay. See how we achieve this from this. See here. This. Now put the value of function here. That is let me do this. this problem. This here. This is different than this. I already told you, this is the amplitude of this wave function. This. Instead of this, I put this. Plus V, this, and this. Remember one thing. Here we have to differentiate twice. And after two differentiation, we will get, from here, we'll get this. E power minus IE T by H cross and C. This plus here, see, here in this function, I differentiated this whole value, this whole function with respect to x twice, second order derivative. And here, just single derivative with respect to time. Remember, here we have to differentiate with respect to x. That's why this remains constant, and this goes, because this is the function of a space. So this goes second, 2 times under derivation, second order derivative, clear? But here, this function goes for derivative with respect to time just one time. And that's why it has no time dependence. It comes out, and this goes under differentiation. Minus IET by H cross E power minus IET by H cross. That would be the differentiation. Now see what we are getting here. First of all, you can see that this and this is equals to, left to this, in the LHS there are two these terms, and this taking common, they will get cancelled. And what we left here? We left here this plus V, this and this. See, I into I square, that is minus 1 and minus. So it becomes plus H cross cancel. And sorry, this is not here because yt is the variable. So what we left here? We left here with this. E, this. That's the time-independent equation of Schrödinger. From here we derive this. Clear? How many? Is there any new comment?
No, there's no comment.
Okay, thanks for watching. You are watching in my live. That's very appreciating, and I'm glad to know this.
There are other videos of relativity and quantum in our
Yes.
channel.
Over my channel, there are videos related to our works on electron spin, Dirac's equation, and my own works with related to electron spin. Why electron has 1/2? How we physically interpret 1/2, half integral spin to electrons, and time dilation, length contraction, relativistic approach to twin paradox, and a lot of integration videos. That is over my channel. You can watch it, view it, and suggest me what is lagging there. We appreciate your suggestions. See, we have achieved time-independent form Schrödinger's equation by time-dependent form Schrödinger equation. This. Now, what is the importance? I already told you that it is quite handy, quite easy to use. That's why they derived this. But the real form is this. This will give you not exact, but this form, time-dependent form of Schrödinger equation, will give you particles matter wave analysis, deeper analysis. But this is just easier way to interpret the particles matter wave function. And this term has no time derivative, means we cannot take a space and time together, means you cannot plot all the information of wave in a space at all the time. You have to deliver information at a certain time. And at that time, it's just like this. Suppose you're moving in a way. You're moving through some... It's like that if you're moving through a city, garden, roads, anywhere, and you're clicking photos. What does it mean? You click the entire space for some particular moment of time. You cannot capture all the moment of time at once. You click the photo, you have all the information of that space in that particular time. That's the quantum mechanics. You cannot give all the information of a space in all the moments of time. Means in some particular time. And that is this. And it is quite easier to use. Now here, see. How many? Okay. Now see here. Let me raise this. I'll sort it off his face. How long it has been? Let to finish half an hour. 5 or 10 minutes more. What?
The picture clicking thing, explain it once.
Okay, see this. See, time-independent form of Schrödinger equation is telling you about the matter wave particle, a matter wave function of the particle with its information of space and time both. That's why space and time. But while time-independent form has no time component, it just has space component. Why is it? See, it has both the things, space also and time also, and in each and every moment. And in quantum mechanics, it's quite confusing that you cannot deliver all the information of a space of all the moments of time. That's why, to make the easier and to try to understand the quantum behavior of particle or matter waves easily, they switched one. They keep the time constant and analyze all the space properties. That's why this. It's like, means they hold the time, fix the time. I do not have to change the time and get the information about the space of the matter wave in non-relativistic speed. That is this. It's like, suppose you are moving through a park, through a highway, and you are clicking photos. Means you have information of the entire space that comes in your frame, but in a one single particular time. So Schrödinger equation is useful in that way. If you are taking entire space information within all the moments of time, then Schrödinger equation is incomplete there, or it is unable to explain everything. And that's why we need higher Dirac equation or some higher quantum mechanics, like a string theory or these things. You can also tell me that if we record the whole space, our journey, it means that we have all the information of a space also, and in the all moments of time. Yes, but that makes that type of approach, taking a space information and time information together, will make the quantum mechanics highly uncertain. And today's live is related to what is time dependent and why we need time independent. And that's why to explain particles in non-relativistic speed, they use time independent equation easier than time, because what? This is the information in one moment of time. Clear? This is matter wave function. Okay? It has two forms. It has two components. One is amplitude component and is the phase component, that is time. So amplitude component is this. So this is the amplitude component of this matter wave function, and we call it eigenfunction. Remember, this is not matter wave function, this is eigenfunction. Eigen is just a casual name due to German scientists have very high contribution in the development of early quantum mechanics. That's why eigen means a characteristic, means understanding matter wave function is very confusing even at that time. That's why they take some strong characteristic, a space-like nature of this function as eigenfunction to explain the particles in non-relativistic speed. Eigenfunction. This is eigenfunction. So this equation has eigen as a function. This. Now, there are some properties of eigenfunction. That is, this is 1 continuous, and let me check from my works. What is this? I'm telling you. There is not 1 but this is continuous. What is the meaning of continuous? This is continuous. It means that differentiation of this with respect to time. No, with respect to time, no, because it is in time independent. There is no time. That's why it must has derivative with respect to its distance, a space variable base. So if this eigenfunction means the amplitude of this matter wave function is continuous, means property of space in x, y, or z axis, means behavior plotting of this matter wave function over x-axis. Remember one thing, nobody has exactly information how matter wave function looks like. Nobody has info. They can't tell you that how is it like longitudinal wave or transverse wave. I explained this in my works on my YouTube channel. On my channel there is a video related to electron spin. There I explained how a matter wave function could look like. So the amplitude part of this matter wave function is continuous. Then its derivative with respect to that axis, that space, is also continuous. Is there anyone?
Yeah.
This. Clear? Now, if we are going to plot this matter wave, we can plot the time component, but we try to figure out the space part, then it must be finite, because we should explain anything which is finite. We cannot explain infinite things. That's why its derivative means that function, this eigenfunction changes in a space is also finite. And this is single valued, means 1, it has just one value. Single valued function in one point of a space, and it has also single valued, is single valued function. What I told you, that this is the complete equation. In non-relativistic case, for a subatomic particle, that could be represented by math wave function. This equation has all the information related to space and time, but we cannot explain both the concepts together in quantum, and that gives highly uncertain analysis. That's why they keep time constant and they use this equation where it's free of time. And this equation is related to the only spatial part of this function has two components. One depends on space, that is x, y, or z axis, and it depends on time. So we fix the time. So this equation depends on the component of this matter wave which is related to space, and that is called eigenfunction. So eigenfunction is continuous and its derivative with respect to that space means change in eigenfunction with respect to the space where it is moving is also continuous. Again, eigenfunction is finite. This is also finite. This is single valued. This is single valued. For undergraduate and college students, you can relate these things. Now, what are the graphical meaning of these three concepts? See here. Graphical.
More than half hour.
Just 5 minutes. Let me raise this. I'm going to finish this now.
See?
This, where this is eigenfunction. See, what is meant by continuous? Let me write this first. See this. As I'm drawing a graph to show you what does this mean. See, oh, you can see that.
Just analyze it. It's more than half hour. Sorry.
See, eigenfunction is over this axis, a graphical representation, and this is the axis through which matter wave function is propagating. This is the function of this. What is the meaning of continuous? Continuous means that, say, if your graph is like this, see, we have two curves. We have two curves. We have one graph like this and this, and they have no connection. They are unconnected. Sorry, they are disconnected. Means they do not have any connection here. It means that they are not continuous. They are discontinuous. For continuous curve, we need
Use the blue one.
no breakings. Understood? This is a continuous curve. But if there will be another curve, then this is discontinuous. Clear? Now see. So eigenfunction must be continuous. Now see here. For single valued, like this, see, at this point of space of matter wave, its amplitude has two values, here also, here also. So if at the same point the matter wave has two values, then that is wrong. So it must has only one wave which is continuous, and it has only one value. So no two curves, just one continuous curve. And at one point in a space it has just one value. That is single valued. And now I'm drawing some, what do we say? Let me draw here. Finite values, not infinite values. See this. See, these two curves, They are not connected means they are disconnected, and at one point of a space they have one value, that's correct. But see, they are coming from infinity means they are not ending. They haven't any definite terminated points. They will reach up to infinity. They're eager to go, and that's not correct. So our eigenfunction has all the three properties. It should be continuous, it should be single valued, and it should be finite in value. And that's for today's life. And in this is not my research work, and this is not research topic. This is the topic just from the undergraduate course, where difference between time-dependent and time-independent Schrödinger equation, and what is the importance, why we need this, why we need to plot this from this, in a very brief way. Okay? So if you want deeper analysis or other research works related to integration, relativity, twin paradox, time dilation, electron spin, Dirac's equation, go to my channel and watch other videos. So thanks for watching. Like and subscribe my channel. And if you have any comments, any suggestion, any question, you can comment me. I'll be glad to know this. Thanks for watching.